Hi everyone, I'm Dr. E. So today we are going to look at some theory related to the convections and conductions currents. Okay, their densities, okay, and also conductor and conductance. Okay, and also some informations related to the polarizations in the dielectric. So let's begin now. Convections and conductions current. So this part is more like theory. Okay, it's more towards the theories. So now we are talking about, where's my mouse? Okay, we are talking about the convections and also the conductions currents. Currents. I currents. I. Okay, so what is currents? So electric currents, they are generally generated, okay, by the motions of the electric charge. Motion, it means that it moves. So when the Q, okay, charge it move, it generate the electric currents. When the Q didn't move, just static there, there is no current. Okay, so the current through a given surface is the electric charge passing through the area per unit time. For example, now you have a surface, something like this. So now you have a Q, okay, many Q lah, for example. So when the Q pass through the surface, pass through the area, okay, it's a surface area, okay, for a specific time, okay, so the I is equals to dq over dt. Okay, so electric charge passing through the area per unit of time. Okay, how much charge passing through, okay, the area at a specific time. Okay, so this is how we calculate the current. So for example, now you have 1 ampere. Okay, so it means that the charge being transformed at the rate of 1 coulomb per second. So meaning that there is 1 coulombs of charge, okay, in pass through the area in 1 second. This is the definitions of the current. So for the current, just now we say charge, right? So many charge that pass through the area. But for this current density, okay, I think you should be familiar with this density, right? Because previously we have our charge, and then we have our rho x, right? Surface current density, okay, and also we have the line charge density. Okay, so density, okay, density, it means that how many, for this current density J, okay, we represent with J, okay, how much current flow through a planar surface, okay, for one particular small surface. Okay, so if the current delta I, for example, now you have the same area, so now I, okay, say the current flow through this surface. Okay, so the current density is how much current is flowing through, for example, one unique small area of the whole area. Okay, just like this one, how much charge per one unit length, okay, or how much charge per one unit of area. Okay, so you will find that this one, the current density is equals to the currents divided with the surface. So for the currents, we have ampere, right? Just now our unit is ampere. So for this current density, the unit is ampere per meter square. So from the unit, actually you can agak what's the meaning of this current density. So how much current passing through 1 meter square of area, okay, of a planar surface. So this is the meanings, okay, of the current density. So if the current density, so if the current density, we want to take into consideration its directions, because just now when I draw these arrows, right, it is flowing, I mean perpendicular, okay, to the area of the surface. What if it is flowing in this way? Or what if it is flowing this way? If you want to consider the angles of these currents, we have to use this one, okay, where there is a dot product between the directions of the current density, okay, with the surface. It is with the surface. This one means to got directions lah. Okay, this one is just the magnitude. Okay, so from this relationship, if you want to know the currents, okay, that pass through a big area, okay, big area, how much current? For example, I give you well, this is the J pass through this surface, small surface. So what will be the total current that pass through the whole big surface? So you will be integrating the current density, okay, dot product with the dx, okay. So now let's look at convection currents. For currents, we have two types. One is convection currents. Okay, the other is conduction currents. So for convection currents, it normally occurs in the insulator or dielectric. Okay, insulator or dielectric is a material that does not conduct currents. So for this kind of current, we don't call it as a conduction current, we call it as a convection current because it is possible for the charge to move in this medium. Okay, so the example of the dielectric are the liquid, vacuum, gas. Okay, they can be many types of gas. Okay, so when there is a motion of the electrons in this medium, okay, we say that there is a generation of the convection currents. For example, you have a bin of electrons in the vacuum tube. This one is also generating the convection currents. So for this convection current, it doesn't involve the conductor, of course, because it involves the insulator, and it does not satisfy the Ohm's law. What is Ohm's law? Ohm equals to what? V equals to IR. So this is the Ohm's law. So you cannot calculate the voltage by using for these situations by using this Ohm's law. For example, you're placing the convection current here, okay, and try to find out what is the resistance of the vacuum or gas, then you say the voltage is blah blah blah. No. Okay, because it does not satisfy the Ohm's law. Okay, so what is convection current density? So the concept is the same. It's a density. Okay, so we might be start with this. You consider that it's a cylinder. Okay, for example, we draw cylinders. It's a cylinders. Okay, so cylinder with volume charge density of rho v. Okay, inside there are many charge. Many charge. So the charge move along the cylinder axis with an average velocity ux. So if this charging they are move, they are move at the velocity ux. Okay, and in the time interval del t, the element of charge has moved at a distance del x. Okay, so this one, for example, at 1 second, okay, this charge already moved, okay, for a certain distance that we call it as del x. So the total charge particle moved through a surface cylinder perpendicular to the direction of motion in time increment del t is, okay, the total charge, okay, equals to rho v multiply with the rho v. This one is the volume. Is the volume. Okay, don't confuse. It's the volumes. Okay, so this one volumes, you can get it by multiply the area with the length. How much it move, right? This one is the basic formula to calculate the volumes. To calculate the volumes. So if the I is this one, and you put these things over here, put this thing over here. Okay, so this you can simplify it as your velocity. Velocity, which is the ux velocity. Okay, so for the current density, you know you have to divide with the surface, right? This is what. Okay, see, surface. Okay, so it will be equals to J is the current density equals to rho v ux, because this one already move here. Okay, divide with the del x. So this one is the current density of the convection currents. Okay, rho v multiply with the velocity. Okay, velocity. How fast the charge move. Now let's look at conduction currents. So for the conduction currents, it occurs in conductor. Conduction current, conductor. Okay, where there are a large number of free electrons. So for conductors, okay, for example, you have wires. So the charge, okay, in the conductor, Okay, they are free to move. You have positive charge, you have negative charge. Sorry, negative charge, positive charge. Okay, so they are neutral. Okay, meaning that the amount of the proton and also the electron, they are the same. Okay, so when you have the electron move in these conductors, okay, it will generate the conduction current. And for this kind of conduction current, it will follow the Ohm's law. It will follow the Ohm's law. Okay, so when an external electric field is applied to a conductor, so the conduction current occurs due to the drift of electrons. Let me check. I will use this figure to explain. I will use this figure to explain. So you see, this is a conductor. Yeah, this is a conductor. So it has positive charge, negative charge. Once you apply the electric field, so this electric field could be from the surface positively charged, positively charged. You put it here, and the other surface is negatively charged. So there are electric field from here to here. Okay, so when you have an electric field, okay, applied on this conductor, okay, the charge, the electrons and also the protons in the conductor, they will align themselves automatically, okay, due to the attractions and also the repulsions, okay, between the positive charge and also the negative charge. So negative charge, they will all gather, okay, they will all gather at the surface of this side, because of attractions, attraction, positive, negative attractions. And the positive charge, it will not go here because it will repel each other, so it will come to this side. They will come to this side. So this is the meaning for this one. When an external electric field is applied to the conductor, okay, conduction current occurs due to the drift of the electron. So this is the drift of the electrons. Okay, one move to the left side, the other move to the right side. Okay, so the electron inside the conductor experience a force. Okay, so this force formula you already learned it before, which is Q E. Okay, because this is electron, that's why it is negative E. Okay, so this is the force experienced by the charge. But experienced by the charge in the conductor. Okay, so due to the continuous collisions with atomic lattice, the electrons move or drift with average velocity. We call it as the drift velocity. So when this electron then move, right, say they will have frictions. They will have frictions. So this is what we call it as the collisions. And then move with average velocity, we call it as the drift velocity. Okay, which is U, and it is proportional to the applied electric field. So if the electric field is stronger, okay, so the charge movement will be also faster. Okay, will be also faster. Okay, so this is the conduction current density. So they are all simplified to J equals to sigma E. Okay, sigma. So this sigma is actually representing the conductivity of the conductor. Conductivity of the conductor. So for semiconductors, the current flow is due to the movement of both electrons and holes. So the conductivity is given by relating the number of holes, which is the NH, okay, per unit volume, and the hole mobility respectively. This one is for the hole. Okay, this is the mobility, is the U, is the velocity. Okay, so this is for the conduction current density. Okay, this one I already explained to you. Okay, what happens? Okay, so the charge that accumulate on the surface of the conductor. But take note, this is an isolated conductor. What is isolated conductor? Meaning that, for example, you put a conductor or you put the metals on the table. You just put it there. It doesn't connect to anything. This is the isolated conductor. So for this, we continue. Just now, all the charge, they are gathered at the surface over here and also surface over here. So when they gather over here, okay, there exists additional electric field internally within the conductor. So this electric field will be in these directions. because positive, negative, right? Okay, electric field is always from positive to negative. Okay, so you have the EI, internal electric field is generated. So this internal electric field, okay, will be cancelled with the external electric field. So it means that the EI is the same as the EE, yeah. So it cancel each other. So at the end, there is no electric field inside this conductor because cancel already, right? Cancel already. So when this E is 0, your D is also 0. So when your D is 0, according to the Gauss law, your Q is also 0, right? Q is also 0. So the volume charge density is also 0. Volume charge density is also 0. Okay, so this one is the explanations. So when it is 0, there is no potential difference between any two points in the conductor. Okay, for example, this is 1 point, this is 1 point. Okay, you want to, this is point A, this is point B. Okay, what is VAB? Okay, it is 0. Okay, because the electric field is 0, right? When you integrate the electric field, this thing will be 0. Okay, so this one is actually an important thing you have to take notes. Okay, because you will use it later on in the boundary conditions. Boundary conditions. Just now we talk about isolated conductor, but now this one is non-isolated. Non-isolated means that it is connected to something. So look at this case. You have a wire, for example, wires. So you have many electrons, protons, okay, all the charges that are inside this wire. And the end of the wire is connected to a battery. Okay, to a battery. So for the battery, you know, this one will supply positive charges here, and this one will supply the negative charges here. So because of these continuous connections, okay, so negative charger will keep on moving in these directions, and also the positive charger, they will move on in these directions. Continuous movement. Okay, so when a potential difference of V is applied across the conductor, the electric field inside a conductor is not 0. Okay, it is unlike this case. Okay, all the charges, they just gather at the surface. But for this case, right, okay, because of the battery, this one is move continuously, the charges. Okay, so the electric field inside this kind of conductor is not 0. It's not 0 because keep on moving. The negative charge over here will go again. Positive charge here will go again. Okay, so there is no static equilibrium inside the conductor. Okay, so means that no electric field exists in the conductor. Okay, so only if no electric field exists in the conductor. Okay, so since the E is not 0, the free charges in the conductor start moving, thus producing conduction current. Right, when there's charge moving, okay, so you have a conduction current. Okay, so you can calculate the resistance, right? You should know, and also the conductance by referring to all these parameters. Okay, so the directions of the electric field produced is the same as the directions of the current or positive charge or currents. So the directions of the electric field, okay, produced is the same as the direction of the flow of positive charge or currents. So when you see this, negative charge is moved in these directions, so the positive charge is moved in these directions, same as the directions of the electric field and also the direction of the current flow in these directions, in the reverse directions compared to the movement of the electrons. Okay, so this is the meaning of the statement. Okay, so that's all about the conductors and also the convections current, conductions currents. So far, okay, everyone? All right. Okay, we'll move to the dielectrics. What is dielectrics? So the major difference between the metals, which is the conductors, and the insulator is the dielectrics, lies in the numbers of electrons available for conductions of currents. Okay, so the dielectric materials have few electrons available that are strongly bounded to the atom. So for the conductor, we know conductor, okay, positive charge, negative charge, okay, they are randomly distributed, randomly distributed, and they are free to move. They can gather here, and they also can gather here. They are free to move when you apply the electric field. But for the dielectric, okay, the electron and also the proton, okay, they are not as free as the conductor. They are bounded. They are bounded. For example, this one, uh, this one. They are bounded by the atom. Okay, but bounded by the atom. Bounded by the atom. They are not free to move. Okay, they are not free to move. So if you apply electric fields, okay, for example, you apply electric fields to this dielectric, the electron and proton inside the atom, they can just slightly adjust themselves. For example, the proton will be here, the negative will be here. Okay, so they can just slightly adjust themselves. They cannot free like the conductor, or positive here, for example, or negative here. No. Okay, so dielectric material, they have a few electrons available that are strongly bounded to the atom. Okay, these are definitions. Okay, and metals have abundance of free electrons that can migrate through the structure of the material. Okay, so for dielectric material, that can be categorized into the non-polar and polar. Okay, so the example of non-polar materials are such as the hydrogens, the oxygen, nitrogens, and some gases. Okay, so it does not have permanent dipole moments. What is the dipole moments? When the atoms inside the dielectric are polarized in this condition, when you apply the electric field, okay, this we call it as a dipole moment. Okay, it does not have permanent dipole moment. It means that when I apply the electric field, it will become like this, but when I cancel this electric field, it will back to the normal, something like this. So it is not permanent. It happened because you apply electric field. Okay, so it only polarized when apply external field and return to original manner after you remove the external field. Okay, this is the meaning. So for polar material, okay, such as the water, sulfur dioxide, okay, so hydrochloric acid, polystyrene, so it comprises of permanent dipole moment that oriented randomly throughout the interior of the material, which tends to align along the directions of the external field. So even though you have removed the external field, okay, this dipole moment, it doesn't go back to their original shape anymore. Okay, they will remain like this. Okay, so this one is the polar material. Right? Polar material. So let's look at the polarizations in the dielectric. How the charge behave when you apply the electric field. Okay, this is the meaning of polarization. How the atom or how the charge that behave when you apply the electric field. So the effect of electric field on the dielectric. Okay, so you can refer to this one. You can refer to this one. So this one is under the normal situations, normal conditions for a dielectric. So you have a nucleus. Okay, the proton is here, the positive charge here, and the electron. Okay, they are surrounded. Okay, the nucleus, and they are bounded by the atom, like what I draw just now. They are bounded by the atom. So you see, without the electric field, so the negative charge, okay, form symmetrical cloud around the nucleus. Okay, see, this one is what I explained. So what happens when an external electric field is applied? Okay, so the charges, okay, inside the atom, they cannot move freely. Okay, because they are bounded by the finite force. Okay, but the external electric field that can polarize the atom or the molecule in the material by distorting the center of the cloud and the locations of the neutral. So because when you apply the electric field, okay, so the nucleus, it will be adjusted. It won't be located at the center anymore according to the directions of the electric field. So when the direction of the electric field is in these directions, nucleus will be moving here, and all the negative charge, okay, that tends to gather here. Huh? So you have changed the center of the electron cloud. Change the center of the electron cloud. Sorry. Okay, so this one is change the center of the electron cloud. So positive charge is displaced from its equilibrium position. Equilibrium position is the position that it's when there is no electric field, which is at the center. Okay, in the directions of E by the force. Okay, so this one is the force experienced by this proton over here when you apply the electric field. So negative charge also, okay, it will experience forces, okay, but the force is in negative directions compared to the positive charge. So we say that the electric dipole is produced, okay, where the charge positive at the center of the nucleus and charge negative at the center of nucleus cloud. So these situations, right, we some sort like we imagine it, okay, it is like a electric dipole. Okay, you have a positive charge gathered here and all a negative charge gathered here. This one is just illustration. You imagine this one has been changed into electric dipole, something like this. Okay, so when this happen, okay, when there is a movement of the nucleus and also the electron in a dielectric, we say that the dielectric is polarized. It's polarized by the electric field. Okay, so the effect of the such electric dipole induce more electric field called the polarization field, which is weaker than and opposite in the directions of the external electric field, right? So you see, this is the external electric field, you see, and this one is the internal electric field, which is the polarization field. Okay, much smaller than the external electric field, and it can be described by dipole moment as this one. So this one is the polarization field, okay, which is created by the electric dipole inside the dielectric when they are polarized. When they are polarized. Okay, so this D is the distance, Q is the value of the charge. Okay, so you can just imagine there is not only one electric dipole, okay, for a material. So you see, when you for these dielectric materials, when you apply the electric field, all the atoms that will align, okay, align in this direction. So you have many dipoles, okay, 1, 2, 3, 4, 5. So the P total will be the summations, will be the summations between steps. Okay. So now we move on to the dielectric strength. Okay, so what is dielectric strength? So the dielectric strength is the maximum electric field that a dielectric can tolerate or withstand without electrically breakdown. Okay, so this one is the maximum value that we can withstand. So after it breaks, okay, the dielectric will become conductive. Meaning that this one, like, it breaks down, so it runs out from the atom, okay, and it can move freely, okay, and become conductor. So when the electric field in the dielectric is sufficiently large, okay, greater than the breakdown dielectric strength, so it begins to pull the electron completely out of the molecules and the dielectric become conducting. So this is what I explained just now. Okay, so that's all for today. So I hope you get some informations related to the theory that I explained to you just now. Thank you, class.